technical difficulties might be a little too much to switch between the two of us. My name is Natalie. I'm your representative from the Graduate Astronomy Students Association, and I'd like to welcome you this autumn evening to the AstroTour for October. Today we'll be talking about black holes, and I hope that we're all able to learn something. I know I probably will. A few notes just before we begin. Those of you who've joined us before will know that this is not our usual building, but we will still be doing telescopes after the talk, and those of you signed up for planetarium shows will be guided to where you need to go. So if you stick around until after the talk, we'll give you all the instructions about where you need to go to find the right buildings, and there'll be plenty of us to help guide you along the way. We've also given you forms as you filed in. We'll be collecting those at the end, and we have cookies to incentivize their return. Without further ado, I'd like to introduce our speaker for tonight, Nick Tacik, who's going to talk to us about black holes and spaghettification. Take it away, Nick.
Okay, thank you, Natalie. Can everyone hear me okay? Yeah. Yes, great. Okay, so I am a graduate at University of Toronto, as you might have read on the slides here. And one of the things I've studied in my time here is I've studied black holes a lot. And when I went to grad school, it was something I really wanted to study. I've always found them very fascinating, very mysterious objects. That's been drilled into me from all the science fiction I've watched since I was a kid. And who else wants to hear about black holes? Apparently, you guys. So at the end of every tour, we do the little feedback forms, and we ask you what you want to hear about next time. That's a question on there right now. And from the last 2 or 3 years of data, we made a word cloud of everyone's responses. And as you can see, the big winner in there is black holes. So that was another reason why I wanted to do a talk about black holes. Now, in doing the talk, we're going to go on a journey. Okay, so let's go on a journey. It's the year 3162, and humans have colonized the galaxy. It's the future. People are traveling with spaceships. Everything's awesome and great. People are traveling the galaxy. And we're all there together. And what do we want to do? Well, of course, we want to sign up for the intrepid SSBHH, Black Hole Hunters. We want to become black hole hunters. We want to get the prize job on this black hole ship, go around the galaxy looking for black holes, traveling to them, and learning cool stuff about them. Okay, but they won't let just anyone aboard the SSBHH. Not everyone can become a black hole hunter. They only take the best of the very best. So the first thing we have to do if we want to get into if we want to become a black hole hunter is we have to enroll at BHU, Black Hole University. We have to go there, we have to pass all our classes, get good grades, graduate, and then we'll be able to become full-on black hole hunters. Okay, so we get to BHU, we do the Frosch thing, and then we go to our classes. Yes, they still have Frosch in 3162. Okay, so we get to our first class, and what do we learn about? Well, we learn about gravity. All in all, black holes are objects of gravity. So first thing, we have to learn about gravity. And to start, we have to learn about Newtonian gravity. This was Newton's theory of gravity that he came up with many centuries ago. And how does it work? Okay, so Newton teaches us, he says that gravity is a force between two objects. It's an attractive force between two objects. I'm an object, and say Natalie's an object, and we have an attractive force. It's platonic, and it pulls us together because we have mass. But neither she nor I are very massive, so we don't see it that much. But when you have more mass, like you have an object like the moon or the sun or the earth, something with a lot of mass, then you can really see its gravitational effect. So Newton says if you have more mass, you have more gravitational attraction. But similarly, the further you go away from the mass, the less the gravitational attraction becomes. The further you get away, the weaker the force is. Okay? And this force Newton discovered is the same force that keeps the planets in orbit around the sun, right? The sun's gravity keeps them in orbit, but it's also the same force that keeps us grounded on Earth. The Earth's gravity pulls us towards the center. Okay, so that's all we've had to learn from Newton. And next we move on to learn about general relativity, which is Einstein's theory of gravity. And we actually have a real-life hologram of Albert Einstein here to teach us about it. Okay, so before Einstein, everyone around thought gravity was solved, you know, with Newton, and they thought they had it. But Einstein came around and really introduced a paradigm-shifting theory. And this was around in the year 1915. And so the first thing we have to think about when we think about general relativity, which again was Einstein's theory of gravity, is we have to think about space-time. So what is space-time? Well, it's very simple. We take space, which is three-dimensional, and we add time as the fourth dimension. So now we have a four-dimensional surface, which is called space-time. And this surface of space-time is very malleable. We can bend it, we can curve it, you know, you can slow down time, you can shrink distances, you can curve them, you can bend and curve this space-time sheet. Okay, but how do you curve it? Well, you do it with energy and mass. Okay, so like in the picture here, you take a flat sheet of space-time and you put a big ball of mass, like the Earth, in the middle of it. And then the space around it starts curving. And gravity, what we experience as gravity, is actually the manifestation of us living in this curved space-time. And just like in Newton's theory, there are some very sensible rules. If you have more mass, the space-time gets more and more warped. But the further you are away from it, the source of the warping, the less warping you experience. Right, you can see at the corners of the sheet here, they're still pretty flat, but when you get near to the Earth there, then it starts getting curved. Okay, so how does that actually manifest as gravity? Well, the trick is that in general relativity, objects, any objects like people or spacecrafts, planets, light, etc., they're very lazy. They want to move along the shortest paths on this curved space-time. And one way you can see that is in the example of light bending. So in this example, the light comes out from up there, and as it passes by the sun, it goes through the sun's gravitational potential well, and it gets curved by it. It gets bent. And this bending of light is actually one of the first ways that general relativity was confirmed to be an accurate theory. Now this curved surfaces thing, it might seem a bit weird to us, but we actually experience it on Earth. Right? The surface of the Earth is not flat. It seems flat on short distances like this. But you know, when you look out, it's actually a two-dimensional surface. And the shortest path on a two-dimensional sphere like the Earth, it's not a straight line, but it's what's called a great circle. Basically, you draw a circle on the sphere. And one way we see this in our everyday life is with flight paths. So if I want to get from, say, Tel Aviv to New York, the flight path, it's not a straight line, it's a curve. All these flight paths are curves. That's because the shortest distance between the points is not a line, but it's a curve. So the lesson here, when you have a curved surface, you take non-straight paths. And that's how gravity works. And then we learn a bunch of hard math to go along with the general relativity, but we'll ignore that for now. Okay, and next we get to the good stuff. We learn about black holes. That's why we came to BHU in the first place. Okay, so the first thing we need to understand before learning about black holes is escape speeds. And this is a very simple idea. Say I want to launch a rocket from Earth into space. If I shoot it up at about, I don't know, say 10,000 kilometers an hour, it'll go up pretty high, but then it'll come back down. That's because it wasn't going fast enough to escape the Earth's gravity well. And there's a certain critical speed that it has to be going at to escape the Earth's gravity, which for the Earth happens to be around 40,000 kilometers an hour, which is quite fast, but we get it. We can get there. We've launched rockets into space. So there's this critical speed that you need to get to escape a gravity well, which is called the escape speed. Okay, so now for black holes. Imagine if you had an object whose gravity was so immense, okay, that its escape speed was greater than the speed of light. Just imagine that, an object with such immense gravity. Well, we know that nothing can go faster than the speed of light. That's one of the rules we learned about in general relativity. So if nothing can go faster than the speed of light, and the escape speed is more than the speed of light, well, then nothing could ever escape this object. And what would it look like if we were to look at this object? Well, to actually see something, I either need to see light that it's emitting itself, or light that gets reflected off it. But no light could ever come outside of it that hits it, because nothing can escape. So I wouldn't see anything. There would be no light. So what's the absence of light? It's blackness. And this would be a black hole. Now, you can also imagine it in terms of the curved spacetime we were talking about. Imagine you're a particle or a person, and you're at the bottom of this gravity well. And you're trying to claw out. You're trying to claw as fast as you can, as fast as you can. But no matter how fast you go, the gravity is always pulling you down too strongly, and you can never escape. So indeed, black holes are these objects where the escape speed is greater than the speed of light. Nothing can escape from them. Now, we can imagine that there's this surface. It's not a real surface. There's nothing physical there. There's no matter or material. It's just an imaginary surface in space, like a sphere. We can imagine this is where the escape speed is equal to the speed of light. So inside that area, the escape speed is greater than the speed of light, and nothing can escape. Outside, the escape speed is less than the speed of light, and things can still escape. And yeah, that surface where it's equal to the speed of light defines the event horizon. It basically defines the boundary of a black hole. And I'll have a picture for you in a second. Now, at the center of this object, we think, is something called a singularity. And that is where all the mass of the black hole is stored. It's stored inside a single point of infinite density. And we'll talk more about that later. So here's a little diagram. It's actually very simple. So we have this white circle I drew, which is called the event horizon. And that's where the escape speed is the speed of light. Then everything inside the event horizon is a black hole. And once you pass the event horizon, you can't escape. And right at the middle is the singularity, this point, of infinite density. So what does that look like for light rays going by the black hole? Well, these first two light rays on the left, they pass the event horizon, so they can never escape out of the black hole again. They're doomed to go to the middle of the black hole and be there forever. This lucky one on the right, it just skirted by the outside of the black hole. It didn't touch the event horizon, so it can still escape and get away from the black hole if it so wants. Okay, so something that should be pretty intuitive. If you have a more massive black hole, its event horizon will be bigger. So if we took a black hole and we weighed it, and it weighs the same as our sun, 1 solar mass, then the event horizon would be about 3 kilometers from the center. It would be 3 kilometers in radius. And how big is that? Well, it's a scale that you're very familiar with. It's a very human scale. If we go from this building, it stretches south to about the lake and stretches north to about St. Clair. So, imagine you look at the big ball of the sun, you take all the mass in there, and you concentrate it inside this tiny portion of downtown Toronto. Right? You have to imagine these things are incredibly dense objects on average. And something that dense is going to have so much gravity, which is why they have such amazing properties. Okay, so we said 1 solar mass is 3 kilometers, and then it's just a linear relationship. If we had one that was 10 times the mass of our sun, the event horizon would be 30 kilometers. And then that's about, it stretches into the suburbs, into Mississauga and Vaughan, but it's still a very human scale. Okay. And so why are these things called horizons? Well, it's much like the horizons on Earth. It's a very simple idea. Right? Imagine you're at sea, you're on your boat, you're on the lake, and you look out. Eventually there's a point, there's a surface where you can't see anything past there. And that's called your horizon. If you've ever been on a lake, I'm sure you've seen it. Right? So past your horizon, you can't see anything more. And that's just like the event horizon of a black hole. Past the event horizon, you can't see anything from there because nothing can ever get out. Okay, so now we've learned everything about black holes, and it's BHU graduation day. Woo! So we go out and party a bit, but you know, for the last few weeks we've been applying for jobs, and we got onto the SSBHH, yay. And we get called in for our first job as black hole hunters. So we've been called in for our first assignment. That's our boss, Mr. Bossman. And he's giving us our first assignment. It's a very simple job. Okay, we're going to fly out to the nearest black hole. And we just want to measure all of its properties. Okay, so we get in our little spaceship here, and we fly off to the nearest black hole. We're incredibly excited. Now this one happens to be named BH 2031 01JX2. Astronomers were never good at naming things. Okay. But when we get there, it's a really incredible sight. And we're really excited to be black hole hunters. We see the black hole there, and we see all the stars and galaxies behind it, and it's sort of bending the light around it. But you can see right there, you can see the black disk of the black hole. That's what we see when we get there. Okay. So we get in our spaceship, we're in our spaceship, and we want to measure the properties of this black hole. Now to be safe, we try to park well away from the event horizon. We park 150,000 kilometers away. That's about half the distance from the Earth to the Moon. So it's a pretty good distance, but you know, we can still see it. We can still see what's going on. And then we start orbiting the black hole in a circular orbit. Okay. As we're orbiting, we look up at the stars, and we see as we move, they change where they are in the sky. They change their patterns. We keep looking at them, we notice that this pattern changes regularly every 5 minutes. So then we know how fast we're going around the black hole. We know our orbital period. We know we're going around every 5 minutes. Okay, so we know how far away we are from the black hole, and we know how fast we're going around. So using Newton's law of gravity that we learned at BHU, we can deduce the mass of the black hole. And it turns out to be 10 times the mass of our sun, 10 solar masses. This little circle with a dot, it means like our sun. So this is 10 times the mass of our sun. Cool. So now we know its mass. And then we take our black hole database, and we look this one up. And we see, indeed, astronomers thought it was a 10 solar mass black hole, and we just confirmed it. We also saw it was born in a supernova in the year 2650. So I'll tell you a bit of a story about the life of this black hole. It started out its life as a high mass star. It was a very blue, very heavy star. It weighed about 30 times the mass of our sun, and it was glowing really, really, really hot. It had a temperature much higher than our sun. But it was glowing so hot, it used up all its energy very quickly, in about 1 million years, which in astronomical terms is very, very quickly. Most things are billions of years. Okay, and then as it ran out of its nuclear fuel, it had nothing to burn. It had no pressure source to support itself against the immense gravity that was pushing down on it. And with no pressure source, it started collapsing, it started collapsing, it started collapsing. And it squished down. You put all this energy in a tiny little place, and then it explodes into this giant supernova. And for a few-week period after that supernova, this whole area shines brighter than the rest of the whole galaxy combined. It's a very bright event. It was spectacular. And, but it doesn't eject everything out in the supernova. It leaves behind the core of the star, which continued to collapse under gravity. And it collapsed into the smallest thing it could, the densest thing it could. which is a black hole. And that's how we ended up with this black hole. Okay. So we continue observing it. We look at the disk of the black hole and we carefully measure it very carefully. And we see that it's a perfect circle on the sky. Okay, so why is that important? Well, if the black hole were spinning, now black holes can either be spinning or not spinning. If it were spinning, it would look more like an egg, like an oval. It would start bulging at the equator. This is true of anything, right? If you take a sphere and you spin it, like the Earth, it starts bulging at the equator. That's true on Earth, and it's true for black holes. But this one, we measured that the horizon was perfectly circular. And so we infer that it's not spinning. Okay, so now we know its mass, and we know it's not spinning. Now, one of us proudly proclaims, I now know everything there is to know about this black hole. It's a very bold statement. How do they know this? Well, at BHU, we learned about something called the no-hair theorem. Okay? So the no-hair theorem, it says that all of a black hole's properties only depend on 3 different things. 1, its mass. 2, its spin. And 3, its electric charge. A black hole is not allowed to have any other properties. Okay, so we're smart people. We figure out that this black hole probably has no charge, okay? If it did have an electric charge, let's say a positive charge, then it would start attracting negative particles towards it, right? That's how electric charges work. Positive attracts negative and vice versa. And then it would bring in all those negative particles towards it, and then that negative charge would cancel out with a positive, and then it would have no net charge at all. So in general, objects in the sky usually don't have an electric charge, and black holes are no exception. So we can safely conclude it has no charge. And now we looked at the picture of the black hole disk on the sky. It was a perfect circle, so we decided it wasn't spinning. And then that leaves only mass, which we measured from our orbit to be 10 solar masses. So now we know everything about this black hole. Okay? And that's kind of a profound thing, right? Black holes are these very simple objects that you can describe with just such little information. Like if I wanted to tell you everything about the Earth, then I would have to tell you a whole lot, right? The Earth has mountains and valleys and oceans and a core and these layers of rock and people and lights and an atmosphere, all this stuff. Right? I would need much more than 3 numbers to tell you everything about the Earth. But for a black hole, you can tell everything with just these 3 numbers. Pretty cool, huh? Okay, so now we've measured all the black hole's properties. That was our mission, so now we head back. Mr. Bosman says, good work on measuring everything about that black hole. Now it's time for your next assignment. Okay? The evil Galactic Lord Zwicky has been active in the Omega sector. He has found a system just like our solar system. And he went there and he took out the sun from that solar system and he replaced it with a black hole that happened to have the exact same mass as that sun. And he's worried that some of the planets might get sucked into that black hole. And then, we can never mine them for minerals or whatever we plan to do. That's not our business, that's his business. Okay, so let's go check it out and see what happened in the Omega sector. Okay, so we get in our spaceship and then we fly off to the Omega sector. All this space travel, it's a very normal activity in the year 3162. Okay, so we get to the Omega sector and we find the black hole, the new black hole, and what do we see? Well, we see a system that looks very much like our own solar system. We see a planet that looks very much like Mercury, one that looks very much like Venus, one that looks very much like Earth, and one that looks very much like Mars. And at the center of them all is a black hole. Okay? So being good humanitarians, the first thing we do is we take out our life detection ray that searches for signs of life, and we beam it around the solar system. and see if there's anything there. But alas, there's no more life here. All the planets are now cold and lifeless. The sun isn't there anymore, it's just a black hole, so there's no source of energy or heat to keep life on these planets going. So unfortunately, everything died. But you know, being scientists, we can't dwell on that too much. Okay, so we take out our measuring instruments and we start measuring the properties of the system. We use our radar dish to measure. We look at the Earth-like planet, and we measure that as 1 AU away from this black hole, which coincidentally is the same distance our Earth is from our sun. And we measure how fast it's moving in its orbit. And we see it'll take 365 days to go around this sun, around this black hole. And using our knowledge of the laws of gravity, we can figure out how fast it's, what the mass of the black hole is, and we determine its 1 solar mass. So as it turns out, the orbital properties of any of these objects, they haven't changed at all, right? So this is an important lesson about black holes that we just learned. When you get near the event horizon of a black hole, things start to get weird. But far away from the event horizon, the gravity of a black hole is just like it was a star with the same mass, right? So all that matters for the gravity is the mass. It doesn't matter if it's a black hole or a star. And now, are we far away from the event horizon? Well, for a solar mass black hole, the size of the event horizon is 3 kilometers. For the distance from the black hole to the Mercury-like planet, it's 52 million kilometers. So 52 million is a lot bigger than 3. So indeed, we're far away from the black hole. So we can conclude that the orbits don't change at all. And we've done our job and measured all the properties. So now we head back to base, and Mr. Boston says, "Good work on that job. I guess I shouldn't have been worried. Black holes don't suck things in." So now we get our next assignment. We have a brand new robot probe and it's built to measure event horizon properties. We want to head to the black hole in the delta sector this time. And we're going to send that probe near the event horizon of that black hole, and it's going to take some measurements, tell us about what's going on there. Okay? So we arrive in the delta sector, when all of a sudden a crazy red shirt from our spacesuit jumps in. He wants to go into the black hole and see what's happening. He's very overeager. Everyone's freaking out on the ship. Oh no, oh no. And as he falls in, things are not going well for him at all. He starts getting squished and squeezed like taffy. Remember taffy? You might have ate it as a child. It's a very stretchy like substance. Or maybe you can think of silly putty, which you might also have eaten as a child. I don't know. But he's being squished and squeezed. And eventually he becomes so squished and squeezed that he can no longer withstand the force. And basically his whole body becomes like a strand of spaghetti. And we say that he gets spaghettified, which, yes, is an actual word. Okay, but he doesn't actually turn into a plate of spaghetti. Okay, so what actually killed him? What is it that's going on here? Why did he die? Okay, so the answer is tidal forces. Okay, so he's falling in feet first, and now his feet are closer to the center of the black hole, closer than his head. And remember, closer means more gravitational force, so there's more force on his feet than on his head, so they get pulled more. And then this results in him being stretched out. And eventually what happens is that he gets stretched so much that he's going to break in two. And then each of those two is going to get broken in two. And then each of those two is going to get broken in two. And so on until everything is just atoms. And then those atoms are going to get broken in two. And then it's all going to be a giant mess of particles that continue to fall into the black hole. So these tidal forces are actually very familiar to us on Earth. It's the same force that causes tides on the Earth, which is why they're called tidal forces. So the moon pulls on the Earth, and it pulls one side, the close side, harder, and the far side less. And so the close side gets pulled more, the far side relative to it gets pulled away, and the top and the bottom, the poles get squished, and it gets flattened out, which is exactly what happened to our redshirt. So one of us does a calculation. Okay, we want to find what's the force difference between the head and the toes. That's the tidal force. So we can do the calculation. The black hole weighs 10 solar masses, like the other one. Mr. Redshirt was 6 feet tall. So the difference in the force was actually 6 million Gs. Now 1 G is the normal gravity we experience on Earth. If you get up to 25 Gs, you start experiencing a lot of pain and possibly death. So 6 million is going to be a lot. Okay, so no wonder he got torn to shreds. Okay, so someone's died, we have to abort our mission, and we head back to base. And Mr. Bossman, he is not happy. He says, our insurance company can't allow us to visit solar mass black holes anymore because the tidal forces are just too much. And we can't risk any more redshirts dying. Okay, but luckily for us, supermassive black holes have much weaker tidal forces. And even more lucky for us, there happens to be a supermassive black hole at the center of our galaxy. So why do supermassive black holes have much weaker tidal forces? Well, remember, they weigh much more. So the event horizon is much bigger, which means when you're at the event horizon, you're much further away from the center. So when you're much further away, the gravity is much, much, much weaker. So that's why the tidal forces are less for a supermassive black hole. Now, how do we know there's one at the center of our galaxy? Well, as it turns out, in the early 21st century, astronomers took observations proving that it was there. And this is what their observations look like. Now, this is real data from the Galactic Center Orbital Models and something group at UCLA, I think. And watch the orbits of these stars, okay? As they get really close to the center, they start whizzing around really fast. Whoop. And you can see they're all orbiting something in the center there. But we can't see what's there. And it looks like whatever's there is in a very, very small space. Okay, so we need something that's very massive. You can calculate the mass based on these orbits. And it turns out to be 4 million times the solar mass. 4 million times. Let that sink in. And it has to be in a very small area. And it can't be emitting any light. And the thing we know that does all those things is a supermassive black hole. So yes, as it turns out, there's a supermassive black hole at the center of our galaxy. All these stars are orbiting it. And it weighs about 4 million times the mass of the sun. Okay. So we get to the supermassive black hole, which is called Sagittarius A star. It's called that because it's in the constellation Sagittarius. Makes a lot of sense. And no redshirts were allowed this time. And we carefully take out our robot probe. His name is Mr. Proby. And we begin to lower him into the event horizon. And he's going to take data for us. Now this time, there are no strong tidal forces. Okay, you can do the same calculation. What's the height difference? And it turns out that the tidal force is 1/100,000th of a G, which is very, very ignorable. So Mr. Proby here, he's going to be fine. He's not going to feel any tidal forces. Okay, so he starts sending out signals to us. He sends out a blue laser at first. He's sending us data with the laser. And at first it appears blue. But as he gets closer and closer, the probe appears, or the laser appears redder and redder. And eventually, the light becomes more than red. It becomes infrared. And then it becomes microwave. And then it becomes radio wave. The wavelength keeps getting longer and longer. And eventually, they surpass the detection of our instruments, and we can't see it anymore. It fades from view. It also sent us back a video of what it saw as it fell into the black hole. And this is really cool, so you can watch it. So he's falling into the black hole, he's spinning around, and it's quite a sight that he sees. The black hole is bending all the light that is coming towards us, which sort of distorts what we're seeing. And light can no longer come to us from horizontal, it all gets bent vertically. So that was quite a show from what he saw. So what happened to him after he crossed the horizon? Well, we can't be entirely sure, right? By definition, nothing that crosses the horizon can ever send us a signal to tell us what they saw. Okay, but we can take a guess. We can take a guess based on what we know about physics. So here's what we think happened. We think Mr. Proby crossed the event horizon. Remember, it's an imaginary surface. He crossed it, and nothing special happened to him. He didn't even notice that he crossed. And then what happens to him is that he's doomed to fall into the singularity, which is this point of infinite density we talked about before. And no matter what, everything that falls into the black hole is doomed to reach the singularity. Right? And we said the tidal forces were weak at the event horizon. But no matter how close or how weak they are, eventually you get close enough that they start becoming big and big, and you will get torn apart before you reach it. So everything is doomed. Poor Mr. Proby. Yeah, it's sad. But we should head back to base. Hey, how do we move around the galaxy so fast anyway? You know, we just went to the center of the galaxy, which is 30,000 light years away. So that journey should take 30,000 years at the speed of light. But we just got there in a couple of minutes. How do we do it? Well, the answer is wormholes. All right? Wormholes are a shortcut through space-time, which are allowed in Einstein's theory of relativity. Right? So imagine you want to get from the yellow region to the blue region. If you went the old school way, which is the path on the left, that journey might take thousands and thousands of years. But if you take this shortcut, through the little throat there, it could be instantaneous. So wormhole is basically this shortcut through space-time, which do exist in this year 3162. Now the trick is that to hold the throat of the wormhole open, you need something called exotic matter, which is physicists speak for matter with negative energy. Now in the year 2015, we don't know of anything like that. But fortunately, scientists invented exotic matter in the year 2754. So we can hold the wormholes open and travel through them freely. Yay. Okay. So we get on our, go through the wormhole, and we go back to Mr. Bosman. He says, good job with that event horizon data. Now we want to head to the Kappa sector. A black hole binary, two black holes in a binary, are about to merge there. Go check it out. And so black hole binaries are a really cool thing. I personally studied them in my research here. I think they're awesome. So when you have two black holes together in a binary, they orbit around their common center of mass. But they don't do that forever. Every time they go around, the orbit loses a bit of energy. It emits these things called gravitational waves, which are little tiny, teeny tiny ripples in space-time. And they travel out at the speed of light. These are called gravitational waves. Then over millions and millions of years, they emit so much energy in these gravitational waves that their orbits shrink and continue shrinking, and eventually they collide. Okay, so these gravitational waves were first discovered by Earth scientists in the year 2016 by a project called Advanced Ligo. Okay, so Advanced Ligo, which is a real experiment, a real cool one, it's designed to detect gravitational waves. It stands for Laser Interferometer Gravitational Wave Observatory. And the way it works is it has these big long arms you can see here, and it shoots the laser beams down the arms. And as gravitational waves pass by, it changes the path of the laser beams. And we look for on the detectors there the presence of these gravitational waves. And so in real life, the first science run of Advanced LIGO just started last month in September 2015. Here's a post on their Facebook page. And this means that the first direct detection of gravitational waves could be coming very soon, which is a kind of profound thing, right? In astronomy, to date, all our detections have been electromagnetic waves, light, normal stuff we're used to. But soon, very soon, we could start detecting gravitational waves. And it opens up a whole new avenue to learn about the universe. There's also a proposed project called LISA, which is like 3 LIGOs in space. But it's hard to get funding for it. And maybe it'll launch by 2050, but I'm hopeful, but I shouldn't be. Okay, so we get in our spaceship and we travel off to the black hole binary. And we see these 2 black holes orbiting each other. Now on board our ship, we have our own very own LIGO, and it's picking up the gravitational waves from the system. And very quickly, with our sophisticated algorithms, we can learn everything about the system. So we measure the masses of both black holes, 10 solar masses. We see they're about 1,000 kilometers apart, and they're going around very quickly, 23 times a second. Right? Think about how quick that is. 1 locomotive. They went around 23 times in that time. Okay, and using our knowledge of general relativity, we can calculate that these 2 black holes will merge in just about 4 minutes. So we got there just in time. Okay, and 21st century scientists, like my supervisor at University of Toronto, simulated what this might look like. And here's a video of it. Okay, so here are the 2 black holes, and they're going around each other. The coloring here represents basically how curved space is. So red is very curved, orange is a bit, and blue is not very much. And they're going around each other, they're going around each other, and we skip ahead a bunch, and they're now very close, and soon enough they get close enough that their event horizons touch, and then they become 1 black hole. And then it jiggles a bit, and then it stops. Now this picture on bottom is the gravitational waves it emitted. And you can see as they get closer and closer, the frequency gets higher and higher. And those gravitational waves are what Advanced LIGO is looking for on Earth. Now a cool fact about this is that when you have 2 black holes merging, as they merge, in the very teeny tiny last second there, the power output that it's releasing in gravitational waves, the energy per second released, is higher than the rest of the stars in our entire universe combined. So this is basically the most energetic event in history, except for the Big Bang. And we got to witness 2 of them merging. How cool is that? Fortunately, we don't get hurt by this giant blast of radiation. The gravitational waves interact very weakly with us, so we're okay. Okay, so we check them out, and we're back to our mission. And we receive a beacon from the evil galactic lord Zwicky. He says, "Fools, I've just stolen the precious galactic titanium diamond. I will destroy it by throwing it in a black hole." Mwahaha. Okay. I think it's time that we do away with the evil galactic lord Zwicky once and for all. So we're going to trick him. Okay. So we tell him, why not use the black hole in the alpha sector? And he says, good idea. Mwahaha. Okay, so why is that a trick? Well, the black hole in the alpha sector is in an X-ray binary. Okay, so what's an X-ray binary? Well, black holes on their own are black. They don't emit light. But sometimes they have another star as their companion. And this is what it looks like when it does. The black hole is there on the right, and it's sort of sucking off this tail of mass from the star. And then that stuff starts orbiting orbiting the black hole in a disk. And it's orbiting really, really fast, so it gets heated up. The particles in there start colliding with each other as they get heated up, and then as they collide, they emit all these X-rays. And they emit them in these beams, kind of, along the axis of rotation of the disk. And so it's emitting a whole lot of energy. Even though it's a black hole, there's all this energy coming from the disk. And they glow quite bright in X-rays. And this is actually how the first black hole was detected. Evil Galactic Lord Zwicky will surely be destroyed by the X-rays there. Let's go check it out from a safe distance. I thought it would be safe. Well, he should have studied at BHU, where he might have learned about X-ray binaries. Okay, so we've defeated the evil Galactic Lord Zwicky. What's next for our intrepid adventures? Well, we'll have to find out next time. Okay, thanks for your time. Okay, so he asked, can you only detect the presence of gravitational waves, but can you detect where they're coming from? And so the answer is we can sort of detect where they're coming from, because there's not just one advanced LIGO on Earth, there's another one, and then there's a different project in Italy, and then another one that might come in Japan. So you use all their signals together, and then you can sort of triangulate where it came from.
You've mentioned like black holes, there's only 3 descriptors for us, but then I guess one of the things is the particles themselves are still within that black hole. And as we looked at the thing about whether the properties of matter versus antimatter actually retain, has that been ever thing to study? Probably.
Okay, so he asked, so there are 3 properties of the black hole: mass, spin, charge, and that's all we can tell from the outside. That only describes the black hole from the outside. But so to answer kind of inside the black hole, there's a bunch of stuff going on, and we're not entirely sure what it is, and I don't know in particular if we know whether or not matter and antimatter retain their properties or not.
That's fine, thank you.
In the back there, you've had your hand up for a while.
Okay, so the question is, what do we think is going on inside a black hole? And that's a very good question. It's very deep, actually. Sort of the simplest answer is that inside the black hole, there's a singularity at the center and nothing else everywhere else, and everything just sort of falls to the center. And that's kind of it. Everything goes to the center, and it just ends its life there. Now there are other theories about what's going on inside. There's a whole bunch of them that I can't get into right now. And they sort of describe more spectacular stuff happening, like the inside of the black hole being really chaotic and energetic, but we're not entirely sure what happens inside.
So the universe is expanding at, as we know, an increasing rate, and matter is being pulled apart. So is it possible that in the future black holes will become so massive that they will become equal to the force that's pulling matter apart and then stabilize the universe? Sorry.
I don't think so, but I don't know of anyone who's ever studied that. I don't know. Black hole gravity is very, very strong at the local level, whereas the galactic expansion, you only see that on sort of really large scales. So I don't think it would ever be strong enough to disrupt black holes.
Yeah, isn't the black black hole, the mass of our sun, as an event horizon of 3 kilometers.
Mm-hmm.
Was that like a simple calculation? Like, it sounds simple.
Yeah, it's a very simple calculation. I can show you after, but basically you multiply the gravitational constant g by the mass of the black hole, and then divide by the speed of light squared, and multiply all that by 2, and then that tells you the size of the event horizon. And so if you want to look up more about that, the keyword there is Schwarzschild radius. I can write it down for you after.
Since the singularity is just a single point, why will a spinning black hole take the oval event horizon?
Well, that's a very good question, and I sort of oversimplified it here. Okay, so the question was, if the singularity is just a single point, why is a spinning black hole, why does it have an oval event horizon? And so I was saying, I did oversimplify it here. For a spinning black hole, the singularity is not actually just a single point, but it's more of a ring, a spinning ring. But yeah, I tried to keep it a bit simpler in the talk here.
Unfortunately, we're going to have to wrap up the questions for now, but you'll be able to come down and talk to Nick after. I just need a few announcements. So as I said at the beginning, we're going to now